There is a distance so small it might mark the edge of reality itself. Scientists call it the Planck length, smaller than a proton, smaller than anything measured. You might think you could zoom in on space forever, smaller and smaller, with no end. But there may be a flaw, a final point where the rules of physics stop working. Try to probe anything smaller, and the universe fights back, crushing your instrument into a black hole. Today we shrink past atoms and protons into a realm where space might be grainy and time might freeze into tiny steps. There, the universe may guard its deepest secret, a limit on how small can be. If you love chasing the edges of what is possible, hit like and subscribe so more of this finds you. Now, brace yourself. We are about to fall past the smallest scale physics can describe. Picture zooming in on your own fingertip closer and closer, past the point where skin turns into cells. Keep going. Cells break into molecules. Molecules break into atoms. Atoms break into protons, neutrons, and something even smaller still. For centuries, scientists assumed you could keep zooming forever. That space itself had no bottom, no smallest piece, no final stop sign. Then, near the year 1899, a physicist named Max Planck ran a set of numbers through his equations almost as a side project, and out popped a distance so strange it seemed to draw a hard line under all of physics. He called it a natural unit of length, built from three of nature's most fundamental numbers: the speed of light, the strength of gravity, and the smallest possible packet of energy, known as the Planck constant. Mix those three numbers together in exactly the right way, and you get a distance roughly 50 quintillion times smaller than a single proton. That number is the Planck length. For most of the 20th century, physicists treated it like a strange mathematical curiosity, a number that fell out of the math but did not seem to mean much on its own. Then quantum mechanics grew up. Then general relativity, Einstein's theory of gravity, grew up alongside it. And when scientists tried to make those two theories agree with each other at extremely small scales, the Planck length kept reappearing again and again like a locked door that every hallway in physics eventually leads to. Today, many physicists suspect that distance grew directly out of two of the strongest theories humanity has ever built, theories confirmed by thousands of experiments, theories that put rovers on Mars and satellites in orbit around Earth with pinpoint accuracy. It may be the smallest length that space itself can support, a flaw beneath which the very words location and distance stop making sense. That is a difficult idea to sit with. Below a certain point, physicists cannot even agree on what a point would mean. Position blurs, direction blurs, the neat picture of space as an empty stage where matter performs starts to fall apart at the edges. When theories that reliable both point toward the same strange wall, scientists pay attention. Some call the Planck length the ultimate zoom limit of the universe. Others call it the seam where two entirely different descriptions of reality, the world of the very large and the world of the very small, are stitched together, and the stitching shows. Nobody has ever measured this distance directly. No microscope built by human hands has come close, and as you will soon see, no microscope ever could. Some physicists spend entire careers chasing that edge, smashing particles together near light speed, hoping to catch even a flicker of what happens down there. Every attempt has come up empty. The distance stays hidden, tucked far below anything our best machines can touch. That silence works like its own clue. The barrier is real, even though we cannot see across it. What we have instead is a number, drawn out of the deepest laws we know, whispering that reality might have an edge. To understand why that edge matters so much, you first need a real sense of how impossibly small this distance actually is. Smaller than anything your imagination has ever had to picture before. Smaller than anything you are picturing right now. Coming up, we shrink that number down into something your body can actually measure itself against, a comparison so extreme it will change how you see every atom around you. A number by itself means nothing to a brain built for measuring football fields, school buses, and the walk to your front door. So let's build this one piece by piece, the way you would climb down a very long ladder. Start with something you can almost picture. A single hydrogen atom, the simplest atom in the universe. One proton with one electron looping around it. That atom is already far too small to see, even with the strongest light microscope ever built. Zoom in past the electron's cloud, down to the proton sitting at the centre. The proton itself is roughly 100,000 times smaller than the whole atom, a tiny nucleus rattling around inside a much larger cloud of empty space. Most students stop the story there, treating the proton as the final, smallest stop on the tour, but the real drop has barely even begun. The Planck length sits below the proton by a gap so enormous that small stops being a useful word. Scientists estimate the Planck length is around 50 quintillion times smaller than a single proton, a number with 19 zeros trailing behind it. Written out that way, it barely registers as real. So try this instead. Imagine you could grab a single atom and stretch it, like pulling taffy, until it became as wide as the entire observable universe, every galaxy, every star, every speck of visible cosmos packed into that one stretched out atom. Now look for the Planck length inside that impossibly huge stretched atom. You will not find a speck too small to notice. You will find something roughly the height of a 40-story building standing inside a universe-sized atom. That is how far below ordinary matter this distance actually sits. Everything you have ever touched, every wall, every phone screen, every drop of water is built from atoms that dwarf the Planck length by that same staggering margin. You're made of enormous structures, towering thousands of stories above a floor so far down that even your smallest particles cannot see it directly. Human beings evolved to judge distance with our eyes and hands, tools built for spotting predators across a savanna, not for tracking distances written with 19 zeros. Our instincts simply were not built for numbers like this, and that gap between what we can imagine and what the math describes is exactly why the Planck length feels less like physics and more like science fiction, right up until you check the equations and find it sitting there, waiting, built from constants nobody invented and nobody can argue away. Every constant that produces this number comes from nature itself, measured again and again in laboratories around the world, agreeing every single time. That consistency is what turns a strange number into a serious question. If a distance this far beneath ordinary matter really marks some kind of flaw, then everything solid around you, your chair, your phone, the ground under your feet, is standing on top of a foundation almost too small to imagine and almost too strange to ignore. Next, we go back to where this number first came from, and the answer might surprise you. It was not built to describe the edge of space at all. Near the end of the 1800s, a German physicist named Max Planck sat down to solve a problem that had nothing to do with the edge of space. Planck was frustrated with how scientists measured the universe. Every unit humans used, the meter, the kilogram, the second, was based on some human-made object or human-made habit. A meter was once defined by a metal bar locked in a vault in France. A second was based on how fast Earth happens to spin, an arbitrary choice tied to one particular planet, not to the universe itself. Planck wanted a system of measurement built from nature's own numbers, ones that would mean the same thing to any scientist anywhere, on any world, using any language. So he gathered the deepest constants known at the time, the speed of light, fixed and unbreakable, the gravitational constant which sets how strongly mass pulls on mass, and a brand new number he had just discovered himself, now called the Planck constant, the tiny packet size that limits how energy can be divided at the smallest scales. Planck combined these three numbers using nothing more than careful algebra, arranging them so their units cancelled out into a pure measurement of distance. He wanted a natural yardstick, a ruler that no human convention could distort, something built purely from nature's own numbers rather than a hunt for the smallest possible length in the universe. The number that fell out of his calculation was almost too small to comprehend, a distance now called the Planck length. At the time, most physicists treated it as a curiosity, a mathematical footnote buried in a paper about units and measurement standards. Nobody in 1899 had the tools, or the theories, to guess what that number might actually mean. Quantum mechanics did not exist yet. Einstein had not yet published his theory of gravity. The two great pillars of modern physics were still decades away from being built. Only later, once both of those pillars were standing, Did scientists realize something remarkable? Every time they tried to describe gravity and quantum mechanics acting together at the smallest, most extreme scales, Planck's old number kept reappearing, popping up in equation after equation like a signature scrawled beneath a painting. It showed up in calculations about black holes. It showed up in early attempts to unify physics. It showed up in the mathematics describing the first instant of the universe itself. A number invented to fix a measurement problem had somehow marked the exact spot where two of humanity's greatest theories both broke down. Max Planck died in 1947, decades before physicists fully grasped what his natural unit of length might represent. He set out only to build a ruler that nature itself would recognize, one that did not depend on a metal bar in a French vault or the spin of one particular planet, and in doing that simple task he may have stumbled onto something far stranger, a hint that space itself refuses to be sliced any finer, no matter which civilization does the slicing, no matter which corner of the universe they call home. What Planck built as a measuring stick, later generations of scientists would come to see as a locked door. The question that took over a century to seriously ask was simple. What happens if you actually try to open it? Some numbers in physics come from a single experiment, a single measurement, a single careful afternoon in a laboratory. The Planck length is different. It comes from marrying three constants that, on the surface, have almost nothing to do with each other. Understanding why they combine into one meaningful distance is like understanding why three completely different ingredients, one from the ocean, one from a mountain, and one from outer space, might combine into a single recipe nature actually uses. The first ingredient is the speed of light, roughly 186,000 miles every second, the fastest anything in the universe can travel. Light sets the ultimate speed limit for information itself, the cosmic rule that nothing can outrun. The second ingredient is the gravitational constant, a number that describes how strongly mass bends the space around it. Every planet, every star, every apple falling from a tree obeys this same constant, governing the largest structures in the cosmos, galaxies bound together across unimaginable distances. The third ingredient is the Planck constant, a number from the opposite end of physics entirely, the strange, jittery world of quantum mechanics, where energy cannot be divided infinitely but comes in tiny, discrete packets. This constant governs the smallest particles, electrons, photons, and quarks, none of which care about gravity in any noticeable way. Light speed rules communication. Gravity rules the larger scales. Quantum mechanics rules the smaller scales. For most of physics, these three domains barely interact. You do not need quantum mechanics to calculate how a bridge holds weight, and you do not need gravity to calculate how an electron jumps between energy levels inside an atom. Yet when you multiply and divide these three unrelated constants in exactly the right combination, their units cancel out perfectly into a single measurement of distance, with no leftover pieces, no awkward extra terms. That mathematical cleanliness works like a signal flare, hinting that these three domains are more connected than they first appear. Physicists describe the Planck length as the distance at which gravity, which normally only matters for huge masses, and quantum mechanics, which normally only matters for tiny particles, are forced to matter equally at the exact same time. Below that scale, you need both gravity and quantum theory working together, describing the same tiny stage at once, and right now, no scientist on Earth has a finished theory that does that successfully. This is why so many physicists treat the Planck length as more than a random footnote. It marks the exact boundary where our two greatest descriptions of reality, the physics of the very large and the physics of the very small, are forced to collide. Imagine two rival map makers, one who only draws mountains and oceans, and one who only draws the streets of a single city block, both trying to draw the exact same tiny patch of land. Their maps do not match, their symbols do not agree. That mismatch, playing out inside real equations instead of paper maps, is exactly what happens when physicists push gravity and quantum mechanics down to the Planck length. Whatever is actually happening down there, cause and effect, space, even time, may need an entirely new kind of map, one nobody has finished drawing yet. Every measuring tool humans have ever built shares one hidden requirement. To measure something, you have to touch it with something even smaller. A ruler measures desk because the marks on the ruler are far tinier than the desk itself. A microscope reveals a cell because light waves are far smaller than the cell walls they bounce off of. This simple rule has driven scientific progress for centuries, and it works beautifully, right up until you try to apply it to the Planck length. The most powerful measuring device on the planet right now sits underground near Geneva, Switzerland, a ring of magnets and detectors called the Large Hadron Collider, stretching about 17 miles in a circle beneath the French and Swiss countryside. Inside that ring, protons slam into each other at speeds close to the speed of light, smashing apart with enough energy to briefly recreate conditions not seen since fractions of a second after the birth of the universe. With all that power, the collider can probe distances down to roughly 100 million billion times smaller than a mile, an almost unimaginable level of precision, and it still falls short of the Planck length by a margin of about 10 million billion times. Picture the entire span of human recorded history, every war, every empire, every invention, compressed down into a single second. The gap between what our best machine on Earth can measure and the Planck length is roughly that same kind of gap. A whole civilization's worth of scale, standing between our sharpest tool and the target. The relationship between energy and measurable distance is baked directly into quantum mechanics itself, through a rule sometimes called the uncertainty principle, far beyond anything a bigger budget or a longer tunnel could fix. To see anything smaller, you need light or particles with a shorter wavelength, and shorter wavelengths always demand more energy. Squeeze a beam of light down tighter and tighter, and its energy climbs, and keeps climbing, with no natural ceiling in sight, at least not one you would want to reach. Reaching Planck length precision would require concentrating energy on a scale that dwarfs anything humanity has ever produced, dwarfs anything a star produces during its ordinary life, and edges disturbingly close to the kind of energy released when a massive star collapses. Engineers cannot simply build a bigger version of the Large Hadron Collider and expect steady progress toward this goal. Even a collider circling the entire planet wall to wall would still land nowhere near the Planck length, still separated from it by a staggering, almost mocking distance. So the question shifts. If brute force measurement is off the table, is there any way, even in theory, to actually probe this length? Some physicists have sketched out thought experiments, imaginary machines built entirely out of equations rather than steel and magnets, designed to test what the universe would do if you truly pushed hard enough. The results of those thought experiments turn out to be stranger and more revealing than anyone building the Large Hadron Collider ever expected. What happens when a purely theoretical machine finally gets close enough to touch the Planck length is where this story turns from measurement into something closer to a trap. Picture an engineer, decades from now, designing a microscope unlike anything built before, a device meant to finally catch a glimpse of the Planck length itself. On paper, the plan looks almost simple. To see something that small, you need light, with an extremely short wavelength, and to get an extremely short wavelength, you need to pour enormous energy into a single, tightly focused beam. So the engineer keeps adding energy. More power, tighter focus, shorter wavelength. Each upgrade nudges the beam a little closer to the target, the same way turning a dial slowly zooms a camera lens closer and closer to a subject too far away to see clearly. For a while, this strategy works exactly the way physics textbooks predict. The beam's effective resolution improves, the wavelength shrinks. The engineer edges closer to distances no human instrument has ever probed. Then something strange begins to happen, as the energy keeps rising toward the levels needed to approach the Planck length. Concentrating that much energy into a space that's small does something gravity has been threatening to do the entire time. It starts warping the space around the beam itself. Mass and energy are the same currency in Einstein's universe, connected by his famous equation relating energy and mass. And enough energy packed into a small enough volume behaves exactly like enough mass packed into a small volume. Past a certain point, that concentrated pocket of energy becomes so dense that its own gravity takes over, curving space so sharply that light can no longer escape. The engineer's microscope seals itself inside an event horizon and becomes a black hole, hiding the very point it was built to reveal. This happens no matter how carefully the beam is built, no matter how advanced the technology becomes, a hard limit written directly into the relationship between energy, mass, and gravity, one that no future engineering breakthrough can root around. Physicists sometimes describe this as nature's own security system, a built-in trap that punishes any attempt to look too closely at the smallest scales. Try to focus enough energy to see distances near the Planck length, and the universe responds by hiding the answer behind an event horizon, the one boundary in physics that famously refuses to let information back out. Even in principle, even with technology far beyond anything humans currently possess, this trap cannot be avoided using the ordinary rules of energy and light. That single fact turns the Planck length from a difficult engineering target into something closer to a locked vault, one where the harder you push against the lock, the more thoroughly it seals itself shut. Some physicists find this deeply frustrating, a twist that keeps the deepest questions about reality permanently out of reach. Others find it thrilling, a clue in its own right, proof that gravity and quantum mechanics are locked together in a genuine, unavoidable collision at the smallest scales, rather than simply neighbours sharing a quiet border. If nature designed a wall this effective, purely as a side effect of ordinary physics, then whatever lies behind that wall must be tangled up with some of the deepest secrets the universe is still keeping. And if brute force measurement always ends the same way, sealed behind an event horizon, then the only path forward is rethinking what space itself is actually made of. Let's slow down and sit inside that failed experiment for a moment, because the details matter more than they first appear to. Physicists have a name for the exact point where an attempted measurement collapses into a black hole. They call it the Planck energy, the specific amount of energy where the wavelength of your probing light and the size of the black hole it would create become exactly the same. Below that energy, your beam of light is too weak to warp space in any noticeable way, and normal physics applies. Above that energy, gravity wins completely, and any light aimed at the target simply vanishes behind an event horizon, instead of bouncing back with information. Right at that crossover point sits the Planck length, the exact distance where these two competing effects, quantum uncertainty demanding shorter wavelengths and gravity demanding an event horizon, cancel each other into a perfect standoff. This is why so many physicists treat the Planck length as more than an abstract number pulled from an equation. It marks the precise spot where two entirely different kinds of physics agree to fight to a draw. Quantum mechanics pushing for infinite precision on one side, gravity slamming the door shut on the other. Nature does not need a committee, a vote, or a warning label to enforce this limit. It falls directly and automatically out of combining Einstein's equations with quantum theory, the same way gravity automatically pulls a dropped phone toward the floor without asking permission first. Some physicists describe this standoff using a memorable image, comparing the Planck length to a cosmic guardrail, a barrier built into the geometry of reality itself rather than into any particular piece of technology. No civilization, however advanced, however many centuries ahead of us in engineering, could build a way around it using ordinary particles and ordinary energy, because the barrier is baked directly into the relationship between space, energy, and gravity. Once physicists fully grasped this trap during the 20th century, the entire conversation around the Planck length shifted. It stopped being treated purely as a footnote from Max Planck's old paper on measurement units, and started being treated as a genuine boundary condition for reality, a place where our current description of both space and time might completely stop applying. If you cannot measure past that point, even in principle, then asking what a location or a distance even means below that scale stops sounding like an engineering question and starts sounding like a philosophical one, except this time backed by hard equations instead of speculation. This single limit, hiding inside a simple thought experiment about a microscope, quietly rewired how physicists think about the deepest nature of space. If space cannot be probed below a certain size, does that mean space simply does not exist as a smooth, continuous stage below that size? Or does it mean something even stranger? That space is still there, but built from pieces so different from anything familiar that our ordinary language for distance and location breaks down completely before we ever get close. That question splits modern physics into several competing camps, each one betting on a radically different picture of what reality looks like once you fall past the point where microscopes turn into black holes. Every physicist agrees on one thing regarding the Planck length: you cannot measure directly past it. What they do not agree on is what that failure actually means. This disagreement splits into one of the most important open questions in modern physics, and it comes down to a surprisingly simple choice. Is space smooth, all the way down, forever, like glass that can be sliced infinitely thin without ever hitting a texture? Or is space grainy, built from some kind of smallest possible unit, like sand that looks perfectly smooth from a distance, but reveals individual grains the moment you get close enough? For most of human history, nobody even thought to ask the question. Space was simply the stage, the empty background where matter moved and events happened, assumed to stretch infinitely smooth in every direction with no structure of its own. Isaac Newton pictured space that way. Even Einstein, when he first built his theory of gravity, treated space and time as a smooth, flexible fabric, capable of bending and stretching but never breaking apart into individual pieces. That smooth picture works beautifully for almost every situation physicists encounter, describing planets, stars, and galaxies with stunning accuracy. It starts to strain, however, the moment you push it down toward the Planck length, the same region where quantum mechanics insists that everything, including possibly space itself, comes in discrete packets rather than smooth, continuous flows. Quantum mechanics already proved this pattern true for other things, once assumed to be perfectly smooth. Light was assumed to be a smooth wave until scientists discovered it also behaves like individual particles called photons, arriving in distinct packets rather than a continuous stream. Energy levels inside atoms were assumed to shift smoothly until scientists discovered electrons can only occupy specific separated levels, jumping between them instead of gliding gradually. Given how often smoothness turned out to be an illusion, once physicists looked closely enough, many researchers now suspect space itself might follow the same pattern, appearing smooth from far away while hiding a grainy, pixelated structure at the Planck scale. If that suspicion is correct, the implications reach far beyond abstract math. A grainy universe would mean there is a true, absolute smallest unit of area and volume, a kind of natural pixel that the entire cosmos is built from, the same way a photograph looks smooth from across a room but reveals individual dots the moment you press your face against the screen. A smooth universe, on the other hand, would mean space really can be sliced infinitely thin, forever, with the Planck length marking only a practical measurement limit rather than a true structural one. These two possibilities run deeper than simple flavor differences. They lead to genuinely different pictures of reality, different answers about what happens inside black holes, different predictions about the first instant of the universe, and different requirements for any future theory that hopes to unite gravity with quantum mechanics. Several major research programs have formed around each possibility, some building entire careers around the belief that space is fundamentally grainy, others building entire careers around defending a smooth, continuous universe, with a few unusual quantum twists layered on top. Neither side has definitive proof yet. What both sides do agree on is this: whichever answer turns out to be correct will change how humanity understands the very fabric beneath everything that exists. And the first serious clue toward answering it came from a physicist who compared empty space to something you would never expect: a pot of boiling water. Empty space sounds like the simplest thing in the universe, a total absence, nothing happening, nothing there. Step outside on a clear night and look up, and the black gaps between stars look perfectly calm, perfectly still, an infinite dark canvas doing absolutely nothing. According to a growing number of physicists, that stillness is a complete illusion, created only because human eyes, and even our sharpest telescopes, are catastrophically too large and too slow to notice what is actually happening down at the Planck scale. The physicist John Wheeler gave this hidden chaos a name in the 1950s: quantum foam. The idea starts with something quantum mechanics already proved true at larger scales, a rule called the uncertainty principle, which says you can never know a particle's exact energy and the exact moment it has that energy at the same time. This is a fundamental feature of reality itself, not simply a limitation of our instruments. One strange consequence is that empty space is allowed to briefly borrow tiny amounts of energy from nothing at all, as long as it pays that energy back almost instantly, faster than any measurement could ever catch it in the act. Physicists call these instant self-correcting energy loans virtual particles, and their effects have been measured in real laboratory experiments, confirmed again and again through careful, repeatable science. Wheeler took this borrowing rule and pushed it down to the Planck scale, where gravity and quantum uncertainty are forced to collide. At that scale, the borrowed energy would be enough, briefly, to warp space itself, punching tiny, short-lived distortions into the geometry of the universe before snapping back smooth again almost instantly, like water briefly bulging and popping in a pot just before it reaches a rolling boil. Wheeler pictured space at that scale as a violent churning foam, riddled with microscopic wormholes and fleeting black holes, blinking in and out of existence so quickly that they never have a chance to grow, never have a chance to swallow anything, never have a chance to be noticed by anything larger than themselves. Zoom back out to human scale, and all of that churning chaos smooths itself into the calm, empty, seeming darkness you see between the stars, the same way a violently boiling pot of water looks perfectly smooth and still if you photograph it from a mile away. This picture remains a proposed idea rather than a confirmed fact, since nobody has built an instrument capable of catching quantum foam directly in action, and as previous chapters made clear, building such an instrument may not even be possible using ordinary methods. Still, quantum foam has quietly reshaped how physicists talk about empty space, shifting it from a passive, boring backdrop into an active, restless, foaming ocean, one running an entire hidden universe of activity beneath a surface too smooth for anything human-sized to detect. If space really behaves this way, then the darkness between every star you have ever looked at is not empty at all. It is boiling every single moment, in a language too small for biology to ever translate. And if space can foam and bubble like that, a new and even stranger question follows close behind. Could that churning foam actually be made of individual countable pieces, the same way ordinary foam is made of individual countable bubbles? Look closely enough at any photograph on a phone screen, and the smooth image dissolves into a grid of individual pixels, tiny coloured squares too small to notice from a normal viewing distance, but absolutely real once you zoom in far enough. A growing number of physicists now ask a startling question inspired by exactly that experience. Could the entire universe work the same way, built from a grid of tiny, indivisible units, too small for anything human-sized to notice, with the Planck length marking the size of a single pixel in the picture of reality? This idea sounds like something pulled from a video game, and honestly, that comparison is not far off, and several serious physicists have used it openly. In this picture, space is closer to a finely woven grid, so fine that everything you have ever touched, seen or measured looks perfectly continuous, the exact same way a phone screen looks like a smooth photograph until you press your eye right up against the glass. The comparison runs deeper than just a fun way to picture things. If space really is built from indivisible units, several strange features of quantum mechanics that once seemed arbitrary suddenly make a lot more sense. Quantum mechanics already insist that energy comes in discrete packets rather than smooth, continuous amounts, a rule confirmed by an enormous mountain of laboratory evidence stretching back over a century. If energy is naturally chunky rather than smooth, many physicists find it entirely reasonable that space, the stage energy moves around inside, might be chunky as well, rather than a strange, isolated exception in an otherwise pixelated universe. There is a very real, very practical reason physicists take this idea seriously instead of dismissing it as pure fantasy. A universe built from indivisible pixels would automatically explain why nothing can ever be measured smaller than the Planck length, the exact wall uncovered back when physicists first tried building a microscope powerful enough to probe it. You cannot find a smaller pixel than the smallest pixel, the same way you cannot zoom a digital photo in far enough to find half of one pixel sitting neatly between two others. The wall stops being a mysterious measurement failure and becomes something closer to an expected, built-in feature of the underlying picture. Serious physicists carefully separate the dramatic pop culture idea of a universe secretly running as a simulation on some kind of cosmic screen from the actual, much more grounded mathematics behind their research. What they are exploring is something more precise: whether the mathematics that already describes gravity and quantum mechanics naturally produces a discrete grid-like structure once you push it down to the Planck scale, the same way ordinary equations for fluid flow naturally produce smooth waves at larger scales, without anyone needing to program either one by hand. Several major frameworks have been built specifically to test this pixel idea using rigorous, testable mathematics rather than speculation alone. One of the most detailed and mathematically ambitious of these frameworks goes further, attempting to describe exactly what those grains would look like, built from something far stranger than squares on a screen, tiny woven loops threading through the fabric of space itself. Imagine for a moment the tightest possible weave of fabric, threads crossing threads, so densely packed that from a short distance away, the whole thing looks like one smooth, solid sheet, rather than countless individual strands. A theory called loop quantum gravity proposes that space itself might be woven together in something remarkably similar to that image, except the threads are made of pure geometry, tiny loops of space itself connected together into a vast, intricate network. Physicists working on loop quantum gravity start from a bold, disciplined choice. Rather than trying to add gravity on top of quantum mechanics as an extra ingredient, the way most other approaches attempt, they take Einstein's equations for gravity completely seriously first, treating space and time as flexible and dynamic exactly the way general relativity describes, and then apply the strict rules of quantum mechanics directly to that flexible geometry itself. When researchers run the mathematics all the way through, something remarkable falls out the other end. Area and volume, the two most basic properties any region of space can have, stop being smooth, continuously adjustable numbers. Instead, they come in specific, discrete steps, the same way energy inside an atom comes in specific, discrete steps, rather than a smooth, continuous range. There is a genuine smallest possible unit of area predicted directly by the math, and its size lands almost exactly at the Planck length, not because any physicist forced that answer into the equations by hand, but because the mathematics produced it on its own once the calculation was carried all the way through. In loop quantum gravity, space is imagined as a vast web of these tiny loops, technically called a spin network by researchers in the field, crisscrossing and connecting in patterns that, when zoomed out to human scale, blend together into the smooth, continuous-seeming space you walk through every single day. Zoom in far enough, however, and the smooth illusion should break apart into the individual threads of the weave, the same way a tightly knit sweater looks like one solid piece of fabric from across a room but reveals individual yarn loops the instant your fingers get close enough to feel them. This picture carries a genuinely testable prediction, one of the very few in this entire area of physics that scientists can actually check against real observations rather than pure mathematics. If space truly has a grainy, woven texture at the Planck scale, then light travelling across truly enormous distances, billions of light years, crossing the entire observable universe, might pick up tiny, measurable delays as it threads its way through countless individual loops rather than one perfectly smooth continuum. Astronomers have already begun searching for exactly this kind of delay in light arriving from some of the most violent explosions in the universe, sudden bursts of gamma radiation blasted out by dying stars collapsing into black holes trillions of miles away. So far, no confirmed detection has been found, and the search remains extremely difficult given how impossibly tiny the predicted delay actually is. Still, the fact that this theory makes any testable prediction at all, reaching from the smallest imaginable scale in physics all the way out to explosions visible across billions of light years, sets loop quantum gravity apart from many of its rivals, and hints that space having genuine texture might not remain a purely mathematical question forever. For most of scientific history, physicists treated space and the objects sitting inside space as two completely separate categories. Space was the empty stage. Planets, stars, and particles were the actors performing on top of it. The stage itself was assumed to have no properties of its own worth studying, no texture, no structure, nothing except pure, featureless emptiness stretching out in every direction. Loop quantum gravity, along with several related theories exploring the Planck scale, quietly overturns that entire assumption, and the shift in thinking runs deeper than it first appears. If space really is woven from discrete loops, with a genuine smallest unit of area built directly into its structure, then space itself becomes an actor in the story, with its own countable pieces, its own internal architecture, its own rules for how those pieces can connect and rearrange. That shift changes how physicists think about several of the deepest puzzles in the field. Consider a black hole, one of the strangest objects the universe produces. Traditional physics describes a black hole's boundary, called the event horizon, as a perfectly smooth mathematical surface, an idealized sphere with no internal structure whatsoever. If space genuinely has a woven, grainy texture at the Planck scale, that smooth sphere is almost certainly an illusion, created by viewing the horizon from far too great a distance, similar to how a soap bubble looks like a perfect, seamless sphere from across a room, but is actually built from a shifting, textured film of molecules the instant you look closely enough. A textured event horizon, built from countable Planck-sized pieces, might explain a puzzle that has troubled physicists for decades: how a black hole can store an enormous, precisely countable amount of information, despite appearing from a distance like nothing more than a smooth, empty void. Consider also the very beginning of the universe. Standard equations describing the Big Bang, when run backward far enough, predict that everything in existence, all matter, all energy, all of space itself, gets crushed down into a single point of infinite density, a mathematical dead end that most physicists suspect signals a breakdown in the equations, rather than a description of anything physically real. If space has a genuine smallest unit of area woven into its structure, that crushing collapse would likely hit a hard floor before reaching true infinity, the same way trying to fold a piece of paper in half again and again eventually hits a physical limit long before reaching a mathematically perfect, infinitely thin sheet. Several detailed models built on this loop-based framework already predict something almost unimaginable. Rather than the universe beginning from a genuine point of infinite density, it may have bounced, emerging from the sudden, explosive rebound of a previous collapsing universe that hit the Planck scale floor and sprang back outward instead of continuing to crush down toward true infinity. None of these ideas have been confirmed by direct observation, and serious researchers in the field are careful, disciplined, and open about that fact every time they publish new results. What has changed, permanently and significantly, is the basic starting assumption. Space is treated less like a blank, featureless stage waiting for something more interesting to happen on top of it, and more like the single most interesting object in the entire universe, with multiple competing theories racing for decades to describe exactly what its hidden architecture looks like, starting from a direction that could not sound more different. Not loops of pure geometry, but impossibly small, vibrating strings. Picture a guitar string stretched tight between 2 points, capable of producing an entire range of different musical notes depending on exactly how it vibrates. Pluck it one way, and you get a low, deep hum. Pluck it another way, and you get a bright, high note. The string itself never changes. Only the pattern of vibration changes, and that single pattern determines which sound reaches your ears. String theory, one of the most ambitious ideas in all of modern physics, proposes something remarkably similar sits at the absolute foundation of everything that exists. Instead of tiny, dot-like particles as the most basic building blocks of matter, string theory suggests reality is built from impossibly small, one-dimensional strands of energy vibrating in different patterns, roughly the size of the Planck length itself. According to this framework, every particle you have ever heard of, electrons, quarks, photons, every single one, is simply a different vibration pattern playing out on the exact same underlying kind of string. The same way a low hum and a bright high note both come from the exact same guitar string, vibrating differently. An electron might be one particular note. A photon of light might be an entirely different note, What looks to us like a universe filled with dozens of different particle types would actually be a single, elegant kind of string, playing an enormous, intricate symphony with the different notes creating the illusion of different particles. String theory grew directly out of a genuine pressing problem in physics, not pure imagination. The mathematics describing gravity and the mathematics describing quantum particles kept producing nonsense, infinite meaningless answers whenever physicists tried to combine them using ordinary point-like particles. Strings, because they have a small but genuine size rather than being an infinitely small point, smooth out many of those infinities in the mathematics, similar to how a wide paintbrush glides smoothly across a canvas, in a way a single sharpened pencil tip, pressed with the exact same force, would eventually tear straight through the paper. Remarkably, when physicists worked through the string theory equations in full detail, a very particular vibration pattern kept appearing among the results, one with all the exact mathematical properties expected of the graviton, the still undiscovered particle believed to carry the force of gravity itself. Gravity emerged naturally and directly from the mathematics of strings, without ever being manually inserted as a separate ingredient, the same way a specific chord emerges naturally from a guitar once the strings are tuned correctly and struck. That single result convinced a significant portion of the physics community that string theory might be pointing towards something real and important about how the universe is built at its most fundamental level. String theory has not gone unchallenged, and the disagreement runs deep within the physics community. Critics point out that string theory currently makes very few predictions that can be tested using equipment humans can realistically build, given that the strings themselves are believed to sit at roughly the Planck length, far beyond the reach of any collider on Earth for a very long time. Some physicists have spent entire careers championing the theory as the most promising path toward uniting all of physics into one framework. Others argue just as forcefully that string theory has drifted too far from anything testable, becoming a beautiful piece of mathematics that may never connect back to a real experiment. Both camps agree on one striking fact, however. If strings are real, then everything you have ever touched is, quite literally, made of music. Sit with that last idea for a moment, because it deserves more than a passing mention before moving forward. If string theory turns out to be correct, then the division between different kinds of particles that every physics textbook teaches, electrons here, quarks there, photons somewhere else entirely, would reflect nothing more than different vibration patterns playing out on the exact same underlying string, the same way a violin and a cello can be built from remarkably similar materials and still produce completely different sounds, purely because of how their strings are shaped, tuned, and set into motion. This single idea carries enormous, almost dizzying implications if it holds up. Every electron in your body, every photon of sunlight warming your skin, every quark locked inside the protons and neutrons that make up the atoms in your bones, would all trace back to the exact same fundamental object, humming in different patterns across an unimaginably tiny scale, one so far below anything visible that it makes even a single atom look like an entire galaxy by comparison. Some physicists find this vision genuinely beautiful, describing it as the closest science has ever come to proving that the entire universe operates according to a kind of hidden, physical music, a set of underlying notes playing out across every scale of existence, from the smallest particle to the largest galaxy cluster. Other physicists remain far more cautious, and their skepticism is not simply stubbornness or a failure of imagination. String theory currently allows for an almost incomprehensible number of possible mathematical variations, sometimes described by researchers using a number so large it dwarfs the total number of atoms in the observable universe. Each variation describes a slightly different possible universe, with different particles, different forces, and different physical laws. Without a clear, reliable way to test which variation, if any, actually matches our own universe, some physicists worry the theory risks becoming untestable in any practical sense, a mathematical structure so flexible it can seemingly be adjusted to explain almost anything, which some critics argue makes it dangerously difficult to ever prove wrong through experiment. This tension sits at the very centre of one of the most important, ongoing debates in modern physics, a genuine, unresolved disagreement among brilliant, serious researchers rather than a settled question with an obvious answer. Loop quantum gravity, the woven, grid-based picture from earlier chapters, and string theory. This vibrating musical picture currently stand as the two most developed attempts to describe what reality looks like at the Planck scale, and they disagree with each other in fundamental structural ways. One pictures space as fundamentally granular, built from discrete geometric pieces. The other pictures space as a stage for vibrating strings, with structure emerging from the string's behaviour rather than from the geometry of space itself. Both camps include brilliant, dedicated researchers who have spent entire careers developing their preferred framework, publishing thousands of papers, and training generations of graduate students to continue the work long after they retire. Neither side has produced the kind of undeniable, repeatable experimental proof that would settle the argument once and for all, and neither theory has yet managed to fully explain and stitch back together everything general relativity and quantum mechanics separately get right about the universe. Somewhere underneath one of these frameworks, or perhaps underneath some entirely different idea nobody has fully developed yet, may lie the true architecture of reality at the smallest possible scale, and one especially strange consequence of that architecture might involve something even more basic than space itself. The very idea of cause coming before effect. Everything you have ever experienced follows one simple, unbreakable rule. Causes come first, effects come second. You flip a light switch, and then the light turns on, never the other way around. You drop a glass, and then it shatters on the floor, never the reverse. This ordering feels so obvious, so built into the structure of reality itself, that most people never stop to question it at all. Down near the Planck length, according to a growing body of theoretical work, that simple ordering may no longer hold together in any way our everyday experience could prepare us for. The trouble starts with a rule explored back in earlier chapters, the uncertainty principle, which says you can never pin down a particle's exact position and its exact momentum at the same time. Push that same uncertainty principle down to the Planck length, and something far stranger happens than a small amount of blur around an object's location. At that scale, trying to pin down an exact position becomes tangled up directly with trying to pin down an exact moment in time, because space and time are not two separate stages in Einstein's universe. They are woven together into a single combined fabric called space-time, bending and stretching together as one connected structure rather than two independent backdrops. If position becomes fuzzy and uncertain at the Planck scale, then the exact ordering of moments in time may become fuzzy and uncertain right alongside it. Some theoretical physicists describe this as a kind of causal fog settling in near the Planck scale, a region where the clean, simple statement "this happened before" that may stop being a meaningful sentence altogether. Two events with an obvious fixed order might have a genuinely uncertain relationship at that scale, with neither one definitively coming first. None of this means your coffee could plausibly get cold before you pour it, or that a dropped glass might unshatter itself back into your hand. Those uncertainties stay locked away at the Planck scale, utterly invisible at the enormous, everyday sizes human bodies and human senses operate at, smoothed out completely by the sheer number of particles involved in even the tiniest object you can see or touch. The implications reach far beyond a strange footnote about very small distances, however. Physics has always leaned heavily on cause and effect as one of its most basic, load-bearing tools, the assumption threaded through nearly every equation, every experiment, every prediction ever made about how the universe behaves. If that assumption genuinely breaks down at the Planck scale, then any future theory of quantum gravity may need to describe reality in an entirely new mathematical language, one that does not assume time flows in one fixed, agreed-upon direction at the very smallest scales, even while our everyday world continues experiencing time exactly the way it always has. Several research groups have already begun building early mathematical frameworks that attempt to describe physics without leaning on a fixed, built-in notion of before and after at the Planck scale, treating causal order as something that emerges only once you zoom out far enough, rather than a fundamental rule baked into reality from the very beginning. This remains one of the most genuinely unsettled, actively debated corners of the entire field, further from resolution than almost anything covered so far in this story. And if time's most basic rule, its simple, forward-marching order, can blur and bend at the smallest scales, then time itself, the steady tick separating one moment from the next, may not be as smooth and continuous as it has always felt. Every clock ever built, From a sundial tracking a shadow across ancient stone to the atomic clocks keeping satellites synchronized in orbit right now shares one quiet, unspoken assumption. Time flows smoothly, continuously, with no smallest possible unit, capable of being sliced into thinner and thinner moments forever, exactly like space was long assumed to work before physicists started seriously questioning that assumption too. Just as the Planck length may mark a smallest meaningful unit of distance, physicists have identified a companion number called Planck time, and it may mark a smallest meaningful unit of time itself. The calculation is almost embarrassingly simple once you already have the Planck length in hand. Take that tiny distance and divide it by the speed of light, the same basic math you would use to figure out how long it takes a car to cross a room if you already know the room's width and the car's speed. The result is a duration so short that even the fastest events in modern physics look like slow motion by comparison. Planck time comes out to roughly 5 sextillionths of a trillionth of a second, a number so far beyond ordinary experience that comparing it to anything human-sized barely helps. Try this instead. The fastest camera shutters ever built by human engineers can capture events lasting roughly 1 quadrillionth of a second, fast enough to freeze individual molecular vibrations in mid-motion. Planck time is still shorter than that blistering shutter speed by a margin of about 10 trillion times. If a single tick of Planck time was somehow stretched out to last 1 full second, that same stretching would take the fastest camera shutter humans have ever built and stretch it out to last more than 300,000 years. Some physicists propose that time itself might move forward in discrete steps at this scale, ticking forward 1 Planck time unit at once, rather than flowing in the smooth continuous stream our senses and our equations both normally assume, similar to how a movie appears to show smooth continuous motion on screen while actually being built from individual still frames, flashing past faster than the human eye can separate them. If that idea holds up, then the smooth flow of time you feel right now, reading this sentence thinking your next thought, would be an illusion built from an almost incomprehensible number of individual discrete ticks, stitched together so tightly and so quickly that no human sense, no human instrument, has ever come remotely close to detecting the gaps between them. This idea remains genuinely unproven, sitting alongside the other unconfirmed ideas explored throughout this story, part of an ongoing, unfinished scientific investigation rather than an established fact ready for a textbook. What makes Planck time so striking is the second half of that same equation. The same basic combination of constants, the same speed of light, the same gravitational constant, the same Planck constant, that produced a smallest meaningful unit of space, also produces a smallest meaningful unit of time, as though space and time really are two faces of one single unified structure, exactly as Einstein's equations have insisted for over a century. If both space and time hit a genuine flaw at the exact same underlying scale, then the most extreme, most violent moment in the entire history of the universe, the very first instant after the Big Bang, becomes the single best place to search for real answers, because that is the one moment in cosmic history when the entire universe itself was small enough and young enough to sit directly on top of that flaw. Run the universe's history backward, past every galaxy merging, past every star igniting, past every planet forming, and you eventually arrive at a moment scientists call the Planck epoch, the very first sliver of time after the Big Bang, lasting no longer than a single unit of Planck time itself. During that almost unimaginably brief window, everything that would ever exist, every galaxy, every star, every atom in your own body, was compressed into a region of space so small it sat directly at the Planck length, the exact flaw explored throughout this entire story. This is the one place in the entire history of the universe where every strange idea from every previous chapter stops being a distant theoretical curiosity and becomes, potentially, the literal physical reality of everything that would ever exist. If space is woven from discrete loops, the Planck epoch is when that weave was tightest, tangled into a shape almost impossible to picture. If space foams and bubbles with virtual particles, The Planck epoch is when that foam consumed the entire universe itself, boiling violently with no larger, calmer backdrop surrounding it, and no distant, still region left to hide the chaos. If causes and effects blur together near the Planck scale, the Planck epoch is when that blur consumed the entire fabric of a newborn universe, still deciding which direction time would even flow. Here is the genuinely humbling part, the detail that keeps professional physicists up late at night, chasing an answer nobody currently has. Every equation modern physics has ever built, general relativity, quantum mechanics, every successful theory tested and confirmed across more than a century of careful experiments, simply stops working once you push backward into the Planck epoch. Run Einstein's equations for gravity back far enough, and they predict the entire universe collapsing into a point of infinite density, a mathematical answer that most physicists interpret as a loud, blaring signal that the equations themselves have reached their limit and broken down completely. Whatever genuinely happened during that first sliver of time, the true starting point of everything, remains one of the biggest open questions left in all of science, a question our current tools are simply not equipped to answer. Some physicists, building on the woven, loop-based picture from earlier in this story, propose the universe never actually began from a true, infinitely dense point at all. It may have bounced, rebounding outward from a previous collapsing universe that hit the Planck scale floor and sprang back rather than continuing to crush down forever. Other physicists, working from entirely different mathematical frameworks, propose the very question of what happened before the Planck epoch might not even be a meaningful question to ask, if time itself only began working properly once the universe expanded past that first sliver of Planck time. In the same way, asking what lies north of the North Pole stops being a meaningful question the moment you're already standing directly on top of it. No experiment has ever directly probed the Planck epoch, and based on everything explored throughout this entire story, no experiment ever may, at least not using any method resembling the ones humans currently know how to build. What remains is a genuine, honest edge of human knowledge, a moment in cosmic history close enough to touch with mathematics, yet far enough beyond direct reach that it may stay permanently locked behind the same wall explored again and again throughout this story. And that locked wall, standing at both the smallest scale in space and the earliest moment in time, is only the beginning of where this trail leads next. Somewhere in the universe right now, matter is falling past a point of no return, crossing an invisible boundary called an event horizon, sliding toward the center of a black hole. Follow that matter in your imagination, deeper and deeper, past the horizon, toward the very middle, and Einstein's equations for gravity make a bizarre prediction. At the exact center, all of that matter, every atom, every particle, gets crushed into a single point of exactly zero size and infinite density. Physicists call this point a singularity, and if you take the equations completely literally, gravity there becomes infinitely strong, space curves infinitely sharply, and the normal rules of physics simply stop producing sensible answers. Infinite anything is almost always a warning sign in physics, a signal that equations have been pushed past the edge of where they still apply. The same way dividing by a number that keeps shrinking towards zero sends a simple fraction rocketing toward infinity, revealing a flaw in the setup rather than something physically happening. General relativity, Einstein's theory of gravity, was built and tested using large, smooth, everyday scales. Planets, stars, entire galaxies bending space in gentle, gradual curves. Nobody designed it to handle a situation where an entire star's worth of mass gets squeezed down to a single, dimensionless point. The theory simply was not built with the Planck length in mind, and that is exactly the region where black hole singularities are predicted to occur, deep inside the event horizon, at a scale far smaller than anything the theory was ever tested against. In the 1960s, physicists Roger Penrose and Stephen Hawking proved something unsettling using pure mathematics. Under very general conditions, any object massive enough to form an event horizon is essentially guaranteed to collapse into a singularity, not as some strange edge case, but as an almost unavoidable outcome once enough mass gets packed into a small enough space. Their proof fell directly out of the pure geometry of collapsing space itself, rather than assuming a singularity in advance. convincing much of the physics community that the equations really were describing something, even if that something clearly could not be literally true. This mismatch points directly back to the wall, explored many chapters ago, the wall where gravity and quantum mechanics are forced to matter equally at the exact same time. A true black hole singularity, squeezed down past the Planck length, is almost certainly the clearest sign physicists have that general relativity alone cannot describe reality at its smallest scales, no matter how successful the theory has been everywhere else. Stars have collapsed into black holes across the universe for billions of years, an event so common that astronomers have now photographed the glowing disks of matter swirling around several of them. Every single one of those black holes is quietly hiding a question modern physics cannot fully answer. What is actually happening at the centre, right at the point where our equations break down and start screaming infinity? Some physicists suspect the true answer has nothing to do with an infinitely small point at all, and that a genuine theory of quantum gravity would replace that impossible infinity with something finite, strange, and built directly from the Planck scale itself, dense beyond imagination, but not truly infinite. If that suspicion holds up, every black hole in the universe might be hiding a genuine physical structure at its heart, one small enough to sit inside the deepest mystery this story has explored so far, and strange enough that nobody has agreed on what to call it yet. Picture two physicists, working in entirely different corners of theoretical physics, both trying to answer the exact same question. What really sits at the centre of a black hole, once you swap out Einstein's infinite point for something the Planck length can actually explain? Their answers could not look more different, and both grew directly out of ideas already explored earlier in this story. One idea comes from string theory. Instead of a black hole hiding a single point of infinite density, some physicists propose the entire interior is filled with an unimaginably tangled, dense ball of strings, packed together at roughly the Planck length, with no true empty space or sharp point anywhere inside. Researchers have nicknamed this idea a fuzzball, and it does something remarkable to the black hole's boundary. Instead of a smooth, featureless event horizon with nothing happening at its surface, a fuzzball's outer edge becomes an active, textured surface, built from the tangled strings themselves, capable of storing information rather than swallowing it into a mathematical dead end. A second idea comes from a loop quantum gravity, the woven, grid-based picture explored several chapters back. That framework predicts a genuine smallest possible unit of area, one that resists being crushed down past a certain point, the same way packing a tightly crowded room of people eventually hits a hard, physical limit no amount of pushing can overcome. Apply that same resistance to a collapsing star, and the crushing collapse that would normally continue forever toward a singularity instead grinds to a halt once it reaches Planck scale density. Some researchers call the result a Planck star, an object so dense it still behaves like a black hole from the outside, complete with an event horizon trapping light, but hiding something entirely different than an infinite point on the inside. An incredibly compact but genuinely finite core. Even stranger, some versions of this idea propose that a Planck star does not stay collapsed forever. After enough time passes, so much time that comparing it to the current age of the universe barely captures the scale involved, the core might bounce back outward, exploding in a sudden burst that could, in principle, release whatever information fell into the black hole across its entire lifetime. Neither picture treats the black hole's interior as empty space wrapped around a single mathematical point. Both insist that something physical and structured must fill that entire region once quantum effects are taken seriously, rather than leaving the deepest part of the object as an unexplained gap in the theory. Neither the fuzzball idea nor the Planck star idea has been confirmed by direct observation, and researchers in both camps are careful, honest scientists who openly acknowledge how far these proposals sit from being proven. What unites them is more interesting than their differences. Both ideas agree that the moment you take the Planck length seriously as a genuine physical flaw, Einstein's impossible infinity disappears entirely, replaced by something strange, dense, and finite instead. If either idea turns out to be correct, then every black hole quietly photographed by astronomers, every dark, silent giant swallowing light across the universe, might be hiding a real, physical object, built from the exact same tiny scale, explored throughout this entire journey, one that may be connected to an even stranger idea. The notion that everything a black hole ever swallows gets stored not inside its volume at all, but smeared flat across its outer surface, like a shadow. Hold a hologram up to the light, one of those shimmering images printed on a credit card or a movie poster, and something strange becomes obvious the moment you tilt it. A flat, two-dimensional surface somehow contains a complete three-dimensional image, full of depth, full of perspective, changing as you move your head, even though the actual information is stored on a surface with no depth at all. In the 1990s, physicists Gerard 't Hooft and Leonard Susskind proposed something almost too strange to say out loud. The entire universe itself might work the same way. The idea started with a genuinely bizarre discovery about black holes. Ordinarily, you would expect the amount of information an object can store to depend on its volume, the three-dimensional space packed inside it. A bigger box holds more books than a smaller box because volume, not surface area, is what normally limits storage. Black holes broke that expectation completely. Careful calculations showed that the maximum amount of information a black hole can hold depends only on the area of its event horizon, the flat two-dimensional surface wrapping around it, not on the three-dimensional volume hiding inside. That single result stunned physicists working in the field. If a black hole, one of the densest, most extreme objects the universe produces, stores its information on a surface rather than throughout its volume, maybe that is a clue about how information works everywhere for every region of space, not only inside collapsed stars. 't Hooft and Susskind pushed that idea to its logical extreme, proposing that all of the information needed to describe everything happening inside any region of space, including the three-dimensional world you're sitting in right now, might actually be encoded on a distant flat boundary surrounding that region, with our familiar three-dimensional reality behaving like a projection cast outward from that boundary, the same way a hologram projects a three-dimensional image from a flat surface. Your chair still holds your weight, and sunlight still warms your skin exactly the way it always has, so this is no claim that the physical world around you is somehow fake. The claim is something deeper and stranger, that the fundamental description of reality, the raw information determining everything that happens, might genuinely live on a lower dimensional surface, with the three-dimensional universe you experience emerging from that surface the same way a fully three-dimensional image emerges from a flat hologram under the right lighting. Few ideas in modern physics sound more like science fiction on first hearing, and few ideas have earned more serious respect from working physicists, precisely because it grew directly out of hard calculations about black hole entropy, measured in units built from the Planck length itself, since each fundamental bit of information corresponds to roughly one Planck area on that boundary surface. If information really is anchored to a boundary, rather than spread through volume, the Planck length becomes the smallest possible unit of information the entire universe can hold. A single pixel not of space, but of reality's own deepest bookkeeping. Proving this idea correct for our actual universe remains one of the largest unfinished projects in physics, and the closest anyone has come started with a much simpler, more artificial universe than our own. In 1997, a young physicist named Juan Maldacena made a discovery that turned the holographic idea from an inspired guess into something physicists could actually calculate with, equation by equation. Maldacena did not attempt to prove the holographic principle for our real, messy, expanding universe right away. Instead, he built a simplified, imaginary universe on paper, one with a slightly different, more mathematically convenient shape than our own, curved in a specific way that gives it a well-defined boundary at its edge, almost like a sphere sitting inside a slightly larger container. Inside that imaginary universe, gravity operates in the usual way, bending space according to Einstein's equations, with objects, black holes, and even the fabric of space itself free to move and warp throughout the interior volume. Then Maldacena showed something remarkable. Everything happening inside that gravitational universe, every particle, every black hole, every gravitational wave rippling through space, could be described with equal accuracy using a completely different theory living only on the flat boundary at the edge. A theory with no gravity in it at all, built instead from ordinary particles interacting the way particles do in familiar quantum field theories. Two totally different descriptions, one full of curving three-dimensional gravity, the other flat, boundary-bound and gravity-free, turned out to describe the exact same physical situation, translated back and forth like two languages describing the same story. This result, now called the ADS to CFT correspondence after the technical names of the two mathematical spaces involved, gave physicists their first genuine working example of holography in action, a real mathematical dictionary letting researchers translate difficult gravity problems into easier boundary problems and back again. Physicists have used this dictionary to make real progress on genuinely hard questions, including some of the black hole puzzles explored in earlier chapters, by translating them into a language without gravity, solving them there and translating the answer back. The catch, a significant one, is that Maldaceno's original example was built for that specially shaped simplified universe, not for the actual universe you live in, which expands outward in a different way and does not naturally come with a clean, well-behaved boundary sitting at its edge. Extending this exact trick to our real universe remains one of the most difficult open problems in the field, and nobody has managed it cleanly yet. Even so, the core lesson refuses to go away. Somewhere in the deep mathematics connecting gravity to boundaries, physicists keep finding hints that space itself, the three-dimensional stage you're sitting inside of right now, might be closer to a very convincing illusion built from information stored somewhere else entirely, translated into the shape, depth, and distance your senses experience every single moment. If that turns out to be true even for our real universe, then everything explored throughout this story, quantum foam, woven loops, vibrating strings, might all be different attempts to describe the exact same underlying reality, viewed from different angles, the same way a shadow, a reflection, and a photograph can all describe one single object without any of them being the object itself. And once space itself starts to look like it might be built from something else entirely, an old, uncomfortable question that has haunted science fiction for decades starts to look less like fiction and more like a real physics problem. If information genuinely sits at the foundation of reality, encoded on some kind of boundary and projected outward into the three-dimensional world you experience, a question naturally follows that sounds more at home in a movie theatre than a physics journal. Could the universe actually be some kind of simulation, information processed by something else entirely, with the Planck length marking the smallest unit that simulation can render, the way a video game world is built from a grid too fine for players to notice during normal gameplay? This question splits cleanly into two very different conversations, and mixing them up causes most of the confusion surrounding this topic. The first conversation is philosophical, built around an argument published by the philosopher Nick Bostrom in the early 2000s. Bostrom pointed out that if any advanced civilization, anywhere, ever develops the ability to run detailed simulations of entire conscious universes, and chooses to run even a modest number of them, simulated universes would vastly outnumber real ones. Statistically, he argued, that would make it more likely than not that any given conscious observer, including you, right now, exists inside a simulation rather than the original, base reality. This argument uses pure logic and probability, and it says almost nothing about the actual physics of our universe. The second conversation is a genuine physics question, far more limited, far more testable, and far less dramatic than Bostrom's philosophical argument. A handful of physicists have asked whether a simulated universe would leave behind any detectable fingerprint, some subtle flaw in how physics behaves at extremely high energies, similar to how a digital photograph, however sharp, eventually reveals its underlying pixel grid if you zoom in far enough, or how a video game world sometimes shows faint seams where one rendered tile meets another. Researchers have proposed that a truly discrete gridded universe might place a subtle upper limit on the energy of cosmic rays, the highest energy particles that strike Earth's atmosphere from deep space, because a calculation running on any kind of underlying grid would struggle to represent energies finer than the grid itself allows. So far, no such limit or telltale seam has ever been detected in cosmic ray data, and most physicists remain deeply skeptical that one ever will be, since a simulation convincing enough to produce our entire universe could plausibly hide its seams far too well for any experiment humans could realistically run. It is worth being honest about where the real science actually stands here. No experiment has found evidence our universe is simulated, and the philosophical argument for it, however clever, makes no specific prediction anyone could test in a laboratory. What survives, stripped of the movie plot version of this idea, is a much stranger, much better supported observation already explored in earlier chapters. Whether or not anything is doing the simulating, our universe genuinely does appear to have a smallest meaningful scale, a resolution limit built directly into the laws of physics themselves, real or simulated. Whether that limit exists because reality is fundamentally discrete, or because something else entirely is rendering it, remains completely unknown, and the search for an answer leads directly into one of the strangest unsolved puzzles in all of physics. What actually happens to information the moment it crosses into a black hole and seemingly disappears forever? Quantum mechanics rests on one rule so fundamental that breaking it would undermine nearly everything else the theory predicts. Information can never truly be destroyed. Burn a book to ashes, and in principle, if you could track every single atom, every photon of light and heat released by the fire, you could reconstruct every word that had been printed on its pages. The information has only been scrambled into an almost impossibly complicated new form. This rule has survived every experimental test physicists have ever thrown at it, across nearly a century of quantum mechanics. In 1975, the physicist Stephen Hawking discovered something that seemed to violate that rule directly, using nothing more exotic than combining quantum mechanics with the physics of black holes. Hawking showed that black holes are not perfectly black after all. Through a subtle quantum effect happening right at the edge of the event horizon, black holes slowly leak a faint stream of particles, now called Hawking radiation, and lose mass as they do, shrinking bit by bit over spans of time that dwarf the current age of the universe. Eventually, given enough time, a black hole should evaporate completely, vanishing from the universe entirely. Here is where the trouble starts. Hawking's calculations showed this radiation comes out completely random, carrying no trace whatsoever of whatever fell into the black hole across its entire lifetime, whether that was ordinary starlight, a spacecraft, or an entire encyclopedia. If that calculation is correct, everything that ever fell into a black hole gets genuinely erased from the universe once the black hole finishes evaporating, information destroyed forever, directly violating the one rule quantum mechanics is not supposed to break. Physicists spent decades treating this contradiction as one of the most serious unsolved problems in the field, a genuine collision between two of humanity's best-tested theories, general relativity predicting the evaporation, and quantum mechanics insisting the resulting randomness should be impossible. Hawking himself spent decades wrestling with this exact puzzle, publicly shifting his own position more than once as new mathematical tools became available. The disagreement grew serious enough that rival physicists placed real, on the record, wagers with each other over how the paradox would eventually resolve, a rare sight in a field usually settled by careful calculation rather than a handshake. Several possible resolutions have been proposed over the years, and each one connects directly back to ideas already explored throughout this story. Perhaps information escapes, smuggled out in subtle correlations hidden within the supposedly random Hawking radiation, correlations too complex for Hawking's original 1970s calculation to catch. Perhaps information gets stored on the event horizon itself, exactly the kind of Planck-scale boundary storage described by the holographic principle a few chapters back. Perhaps a remnant survives at the very end of the evaporation process, a tiny, Planck-sized object holding all the missing information locked inside, similar to the fuzzballs and Planck stars explored earlier in this story. Remarkably, in the years leading up to this very story, several research teams made real mathematical progress on this exact question, using techniques borrowed directly from the holographic boundary methods explored in the previous chapter, finding calculations suggesting information may genuinely escape after all, smuggled out through extraordinarily subtle quantum connections nobody had properly accounted for before. The debate over exactly what this progress proves is still very much ongoing among specialists in the field, and few problems in modern physics show more clearly how tightly the smallest scale in the universe is woven into some of the largest, strangest questions science still has not fully answered. Picture a black hole sitting alone in the depths of space, far from any star, any dust cloud, anything left to swallow. You might expect nothing to happen at all, an object so extreme that light itself cannot escape simply sitting frozen, unchanging forever. Hawking's discovery, explored in the previous chapter, revealed something stranger. Even a black hole with nothing left to feed on is slowly losing mass, radiating itself away particle by particle through a quantum effect happening right at the edge of its event horizon. Here is roughly how physicists explain that effect using ordinary language. Empty space, as explored several chapters back, constantly generates brief, paired bursts of particles and their antiparticle twins, borrowing tiny amounts of energy for an instant before paying it back and vanishing again. Near the edge of a black hole, that ordinary process occasionally gets interrupted in a very specific way. One particle from a pair falls across the event horizon, swallowed forever, while its twin escapes outward into space. Because that escaping particle needed energy to exist, even briefly, and its partner never paid that energy back, the black hole itself effectively covers the debt, losing a tiny sliver of its own mass every time this happens. Repeat that process an almost unimaginable number of times, and the black hole slowly shrinks, evaporating over a timescale so long it makes the current age of the universe look like a single heartbeat by comparison. For an enormous black hole, one holding the mass of an entire star, this evaporation would take far longer than the universe has existed so far, stretching out across a length of time with more zeros than most calculators can even display. For a black hole no more massive than a mountain, by contrast, that same evaporation clock runs dramatically faster, small enough that some physicists have speculated tiny black holes, formed in the extreme conditions of the early universe, could be quietly finishing their evaporation somewhere in the cosmos even now. As a black hole shrinks though, something important changes about how quickly it loses mass. Smaller black holes evaporate faster than larger ones, and as the shrinking accelerates, the black hole eventually approaches a mass and a size that inches uncomfortably close to the Planck scale itself. This is exactly where Hawking's original calculation runs into trouble, and where every idea explored throughout this entire story comes crashing together at once. Hawking's equations, like general relativity itself, were built assuming smooth, continuous space, with no Planck scale graininess, no woven loops, no strings, no boundary storage taken into account. Once a shrinking black hole approaches Planck-sized dimensions, that assumption almost certainly stops holding up, the same way every other calculation in this story eventually runs into the same wall once pushed far enough. Nobody currently has a finished, agreed-upon description of what happens during those final moments of a black hole's life, whether it vanishes completely in one last burst of radiation, leaves behind a stable Planck-sized remnant that never fully evaporates, or does something else nobody has fully imagined yet. Some physicists have proposed searching for the telltale flash of a black hole's final evaporation directly, a burst of radiation from an ancient tiny black hole, finally reaching the end of a process that began long before Earth even existed. No such flash has ever been confirmed, but the search continues, aimed squarely at catching the one moment in the universe where the largest, darkest objects known to science finally meet the smallest scale explored throughout this entire journey. Every idea explored so far in this story, quantum foam, woven loops, vibrating strings, holographic boundaries, has treated space and time as things that exist, even if their exact structure remains mysterious or hotly debated. A newer, stranger line of research asks an even more unsettling question. What if space and time are not fundamental at all, but something built, assembled out of a more basic ingredient the same way a brick wall is built from individual bricks, even though the wall itself looks like one solid, continuous surface from a distance? This idea, sometimes called emergent spacetime, did not begin as a deliberate assumption written into anyone's theory on purpose. It gained serious momentum almost by accident after physicists studying the holographic principle noticed something remarkable buried inside their own calculations, tools that were never originally designed to describe geometry at all. In these boundary-based models, the geometry of space, its shape, its curvature, even how far apart 2 points appear to be, seem to be built directly out of a purely quantum phenomenon called entanglement, the strange connection linking particles so tightly that measuring one instantly affects predictions about the other, no matter how far apart they are separated. Researchers found that the more strongly two regions on the holographic boundary were entangled with each other, the shorter the distance appeared to be between the corresponding regions of space in the interior. Weaken that entanglement, and the corresponding distance stretched out instead. Space may be closer to a byproduct, a kind of visible symptom produced whenever enough quantum information gets tangled together in just the right way. The same way temperature is not some separate fundamental ingredient added to a gas, but an emergent measurement of how fast countless individual molecules happen to be moving. Some physicists have pushed this idea even further, proposing a genuine working connection between entanglement and one of the strangest objects explored earlier in this story: wormholes, the theoretical tunnels connecting distant points in space. A striking conjecture, sometimes summarized by physicists as entanglement equals wormhole, suggests that two black holes sharing a strong enough quantum entanglement might actually be connected by a wormhole running directly between them, with the entanglement and the wormhole serving as two different descriptions of the exact same underlying physical connection, rather than two separate phenomena that happen to occur together. If any version of this idea holds up, the implications reach further than almost anything else explored in this entire story. Space would not simply have a smallest possible unit sitting at the Planck length. Space itself would be a kind of illusion, an emergent stage woven together entirely out of quantum connections, with the Planck length marking the smallest unit of connection needed to weave any wall into existence at all, rather than merely the smallest brick in a wall already standing. This remains one of the most actively researched, least settled corners of the entire field, built on mathematics still being worked out today rather than a finished textbook picture. What makes it worth taking seriously is where it keeps leading. Nearly every serious attempt to understand the deepest nature of reality, no matter which starting point researchers choose, keeps arriving back at information, connection, and the Planck scale. Three ideas that increasingly look less like separate topics and more like different names for the exact same underlying mystery. Albert Einstein built one of his most famous theories, special relativity, around a single, unbreakable rule. Every observer in the universe, no matter how fast they are moving relative to anyone else, measures the exact same speed for light in a vacuum. A person standing still and a person racing past at half the speed of light will disagree about almost everything else: how long a journey takes, how far apart two events happen, even how much time has passed, but they will never disagree about the speed of light itself. That single point of agreement, called an invariant, holds Einstein's entire theory together. Special relativity also predicts something else, a strange side effect called length contraction. Objects moving relative to an observer appear physically shortened along their direction of motion, more and more the closer they get to light speed. This effect has been measured directly in laboratories, confirmed repeatedly using fast-moving particles, and it creates an unexpected headache for the Planck length. If the Planck length really is a fixed fundamental unit of distance, built into the structure of reality itself, then every observer in the universe ought to measure the exact same value for it, the same way every observer measures the same speed for light. Ordinary length contraction says the opposite should happen instead. A fast-moving observer should measure lengths, including, in principle, the Planck length itself, as shorter than a stationary observer would measure. Two of Einstein's own trusted results seem to be pulling in opposite directions, one demanding the Planck length stay fixed for everyone, the other demanding it should shrink depending on how fast you happen to be moving. In the early 2000s, physicists including Giovanni Amelino Camiglia and João Magejo proposed a fix, a modified version of special relativity now called doubly special relativity. Their idea keeps Einstein's original invariant: the speed of light stays the same for every observer, and adds a second one alongside it. In this framework, the Planck length itself becomes invariant too, agreed upon by every observer in the universe regardless of how fast they happen to be moving, the same way every observer already agrees on the speed of light no matter their own velocity. To make both invariants hold true at the same time, the researchers had to adjust the mathematical rules describing how measurements of space and time transform between different observers, introducing subtle corrections that only become noticeable at extremely high energies, far beyond anything current experiments can produce or detect. This remains a genuinely contested idea within the physics community, with some researchers treating it as a promising necessary patch to Einstein's original framework, and others viewing it as an unnecessary complication addressing a problem that a fully finished theory of quantum gravity might resolve in some entirely different way nobody has thought of yet. What makes doubly special relativity worth taking seriously, regardless of which side eventually wins the argument, is the sheer audacity of the question it dares to ask. Is it possible that two observers, one standing still and one racing past at nearly the speed of light, watching completely different versions of the same event unfold in front of them, might still, somehow, be forced to agree on the exact same smallest possible distance in the entire universe? Sit with that question from the end of the last chapter for a moment, because it deserves a closer look before moving forward. Picture two observers watching the exact same tiny event unfold, an event happening right near the Planck scale itself. One observer stands still, watching calmly from a fixed position. The other races past at 99% of the speed of light, close enough to light speed that ordinary special relativity predicts their measurements of length and time should look dramatically different from the stationary observer's measurements. Under ordinary rules, the fast-moving observer should measure distances along their direction of travel as significantly shortened compared to what the stationary observer sees, a real, measured physical effect rather than a trick of perspective. Doubly special relativity predicts something stranger happens once those measurements get pushed all the way down toward the Planck length. Both observers, despite disagreeing about nearly everything else in the event they are watching, the exact timing, the exact positions, the exact energies involved, would still land on the exact same measured value for the Planck length itself, refusing to shrink or stretch no matter how different their two perspectives otherwise appear. Physicists sometimes compare this to two witnesses describing a car crash from wildly different angles, disagreeing about which direction the cars were travelling, how fast the impact happened, even which car hit which first, while somehow still agreeing with total precision on the exact make and model of one particular bolt lying on the pavement between them, a tiny universal fixed point buried inside an otherwise completely disputed scene. This kind of built-in agreement is exceptionally rare in physics, since almost every other measurable quantity depends at least partly on an observer's own motion, which is exactly what makes the handful of true invariants that do exist some of the most closely studied numbers in the entire field. This is more than a mathematical curiosity invented to patch over an inconvenient contradiction. If doubly special relativity turns out to be correct, it would mean the Planck length holds a genuinely special status in the universe, standing alongside the speed of light as one of only a small handful of true constants that mean the exact same thing to absolutely every observer, no matter how they are moving, no matter what corner of the universe they occupy. Some physicists find this idea deeply satisfying, since it would finally explain why the Planck length keeps reappearing throughout physics as a genuine physical flaw rather than a value that shifts depending on who happens to be measuring it. Other physicists remain unconvinced, pointing out that no experiment has yet detected the subtle corrections doubly special relativity predicts, and that simpler explanations might eventually account for the same puzzle without needing to rewrite Einstein's equations at all. The disagreement remains unresolved, sitting alongside several other open questions explored throughout this story, each one waiting on better mathematics, better experiments, or both, before physicists can settle which picture of reality is actually correct. What nobody disputes, regardless of which side of this argument they fall on, is the strange, quiet authority the Planck length keeps demonstrating across nearly every serious attempt to understand the smallest scales of the universe, showing up again and again in theory after theory, hinting that whatever the final true theory of quantum gravity eventually looks like, this single tiny number will almost certainly still be standing at its very centre. Somewhere in the vast library of solutions to Einstein's equations for gravity, sits an idea that sounds like it belongs in a science fiction film rather than a physics textbook. A wormhole, technically called an Einstein-Rosen bridge after the two physicists who first described it mathematically in 1935, is a theoretical tunnel connecting two distant points in space, potentially collapsing an ordinary journey of thousands of light years down into a short walk through a connecting passage. On paper, the mathematics allowing wormholes to exist is completely legitimate, following directly from Einstein's own equations without needing any exotic new physics invented specifically to make them work. In practice, every known solution comes loaded with brutal complications that have kept wormholes firmly in the realm of theory rather than engineering. The tunnel connecting 2 points tends to be violently unstable, snapping shut and pinching off almost instantly, faster than light itself could ever cross through it, unless something extremely unusual props it open. That something, according to the equations, would need to be a form of matter or energy with genuinely negative energy density, a substance that has never been directly observed anywhere in the universe at any meaningful scale, and that many physicists suspect may be forbidden entirely by deeper laws still being worked out. Physicists sometimes describe negative energy density as a kind of cosmic debt, since ordinary matter, arranged however cleverly, can never supply it. This is exactly where the Planck scale re-enters the story. Remember quantum foam from several chapters back? The churning, bubbling picture of empty space, briefly generating tiny wormholes and fleeting black holes at the Planck scale before they snap back out of existence almost instantly. Some physicists have wondered whether those microscopic, naturally occurring wormholes might represent the only genuinely real version of this idea the universe actually produces, tunnels so small and so short-lived that nothing, not even a single particle, could ever hope to cross through one before it collapses. Enlarging one of these fleeting Planck-scale wormholes into something a spacecraft or a person could actually travel through would require controlling physics at exactly the scale. This entire story as shown resists every attempt at direct human control, using energy and precision so far beyond anything currently achievable that most physicists consider the idea firmly outside realistic engineering, now or possibly ever. Time travel connects to this same tangle of ideas in an equally complicated way. Certain theoretical wormhole configurations, if they could somehow be stabilized and manipulated with impossible precision, mathematically permit connections not just across distant space, but across different points in time as well, opening a door toward the kind of paradoxes that have fascinated storytellers for generations. Most physicists studying this area suspect that some deeper law of physics, quite possibly one rooted in the same Planck-scale graininess or causal fog explored earlier in this story, prevents these paradox-generating configurations from ever actually forming in the real universe, even though nobody has proven that protection with complete certainty yet. What remains, stripped of the science fiction excitement, is a genuinely open scientific question rather than a settled impossibility. Wormholes and time travel sit locked behind the exact same wall, built from negative energy, extreme precision, and Planck-scale control that has turned nearly every other idea explored throughout this story from a wild possibility into an unsolved, deeply respected mystery. Step back for a moment from black holes, wormholes, and vibrating strings, and consider the shape of the puzzle this entire story has been circling from the very first chapter. Physics currently runs on 2 separate rulebooks, and both of them work extraordinarily well within their own territory. General relativity, Einstein's theory of gravity, describes the large-scale universe with breathtaking precision, correctly predicting the bending of starlight around the sun, the existence of black holes long before anyone photographed one, and the exact timing corrections needed to keep satellite navigation systems accurate to within a few feet anywhere on Earth. Quantum mechanics, meanwhile, describes the small-scale universe with equally stunning precision, correctly predicting the behavior of electrons, photons, and every particle inside every atom in your body, confirmed across nearly a century of laboratory experiments that have never once caught it making a genuine mistake. Here is the problem physicists have wrestled with for generations. These 2 rulebooks are built from fundamentally incompatible mathematical assumptions. General relativity treats space and time as smooth, continuous, and perfectly predictable, bending gently in response to mass and energy, following rules that always produce one single definite outcome for any given situation. Quantum mechanics treats reality as fundamentally probabilistic and uncertain, describing particles that do not have definite positions or definite properties until the exact moment they get measured, governed by rules built entirely around chance and uncertainty rather than smooth, guaranteed predictability. Most of the time, physicists simply do not need both rulebooks operating in the same calculation. Calculating a rocket's trajectory to Mars uses gravity alone, no quantum mechanics required. Calculating how electrons jump between energy levels inside an atom uses quantum mechanics alone, no gravity required in any meaningful way, since gravity is astonishingly weak compared to the other forces at that scale. The trouble starts precisely at the Planck scale, the exact region explored throughout this entire story, where an object can be simultaneously massive enough for gravity to matter and small enough for quantum uncertainty to matter, forcing both rulebooks to apply to the exact same situation at the exact same time. Try to run the math, and the two theories do not simply disagree. They actively contradict each other, producing nonsensical, infinite answers rather than two competing but sensible predictions physicists could test against each other. This collision shows up in exactly the places explored throughout this story. The center of a black hole, the first instant after the Big Bang, and any attempt to build a device precise enough to directly probe the Planck length itself. Solving this problem, finding a single, unified theory of quantum gravity that correctly describes both the smooth curves of general relativity and the probabilistic uncertainty of quantum mechanics at the exact same time, ranks among the most difficult, most sought-after goals in the entire history of science. Generations of brilliant physicists have dedicated entire careers to this single problem, producing remarkable partial progress, loops, strings, holographic boundaries, emergent space-time, without a single one of them yet producing a complete, tested, universally accepted answer. Whoever eventually solves it, if anyone ever does, will not just be patching a technical disagreement between two old theories. They will be handing humanity its first genuinely complete description of reality, from the largest galaxy down to the smallest possible speck of space. Physics has chased unification before, and won more than once. In the 1800s, scientists treated electricity and magnetism as two separate, unrelated forces, until James Clerk Maxwell discovered they were actually two faces of one single phenomenon, electromagnetism, described by one unified set of equations rather than two disconnected ones. In the 1970s, physicists achieved a similar merger, showing that electromagnetism and the weak nuclear force, the force responsible for certain kinds of radioactive decay, are also two faces of one deeper force, called the electro-weak force, that only splits into two seemingly different forces once the universe cools down below an extremely high temperature. Each time, physicists successfully merged forces that once looked completely separate. The resulting theory turned out simpler, more elegant and more predictive than the two disconnected theories it replaced. Today, physics recognizes four fundamental forces governing everything that happens in the universe: electromagnetism, the weak nuclear force, the strong nuclear force holding atomic nuclei together, and gravity. Three of those four, electromagnetism, the weak force, and the strong force, have already been folded into a single, well-tested mathematical framework called the Standard Model, one of the most thoroughly confirmed theories in the history of science, verified through decades of experiments at particle colliders around the world. Gravity remains the holdout, the one force that has stubbornly refused every attempt to fold it into that same unified framework, precisely because gravity is described by general relativity, a theory built on smooth, continuous geometry rather than the same quantum rules governing the other three forces. A genuine theory of quantum gravity, the kind of theory this entire story has been circling from every possible angle, would complete the pattern started by Maxwell nearly 2 centuries ago, finally uniting all four fundamental forces into one single, elegant framework, a true theory of everything, capable in principle of describing every particle, every force, and every interaction in the universe using one unified set of equations. There is a tantalizing clue suggesting this unification really might happen, and it points directly back to the Planck scale. When physicists calculate how the strengths of the three already unified forces change at higher and higher energies, all three curves bend toward each other, creeping closer and closer to a single shared value, though they do not quite meet perfectly using the standard model alone. Several proposed extensions to the standard model predict those three curves would meet in a single, precise crossing point if you extend the calculation far enough, and that crossing point lands at an energy tantalizingly close to the Planck energy itself, the same extreme scale explored throughout nearly every chapter of this story. Physicists call this predicted meeting point a grand unified energy, and reaching it experimentally would require a particle collider vastly larger than anything humanity could hope to build using current engineering, far beyond even a collider circling the entire planet. Some of these same extensions predict protons, long assumed to be perfectly stable, might eventually decay after spans of time that dwarf the current age of the universe, a prediction physicists have spent decades quietly testing for using detectors buried deep underground, without success so far. If that convergence is more than a coincidence, gravity might simply be waiting for physicists to reach the right energy scale, the Planck scale, where all four forces finally reveal themselves as different faces of one single unified force, the same way electricity and magnetism once looked like two separate mysteries before Maxwell showed the universe had been speaking one unified language all along. Every idea explored throughout this entire story, quantum foam, woven loops, vibrating strings, holographic boundaries, doubly special relativity, points toward the exact same unsettling conclusion. Reality may have a built-in resolution limit, a genuine flaw beneath which certain questions that feel completely natural and reasonable at ordinary human scales, simply stop having meaningful answers. This is a strange kind of limit, unlike almost anything else science has encountered before. Most limits in the history of science have been limits of measurement, boundaries created by imperfect instruments, imperfect technology, imperfect human effort. Boundaries that history has shown, again and again, eventually fall to better engineering and cleverer experimental design. The speed of sound once seemed like an impossible wall for aircraft, until better engineering broke straight through it. The idea of splitting an atom once seemed impossible too. Not every barrier in physics has eventually fallen to clever engineering, however. The speed of light itself has stood as a genuine, unbroken limit for over a century, confirmed by every particle accelerator ever built, never bent, never exceeded, no matter how much energy engineers pour into the attempt. The Planck length, if the deepest interpretations explored throughout this story turn out correct, may represent something categorically different, a limit built directly into the structure of reality itself, rather than into the limitations of human technology, a wall that no future civilization, however advanced, however many thousands of years ahead of us in engineering, could ever engineer its way around, because the wall is the edge of the map itself, not a technological problem waiting for a clever solution. Sit with what that would actually mean for a moment. Questions like, where exactly is this particle located, or what happened one instant before this event, questions that sound like they should always have some kind of answer, however difficult to find, might genuinely stop making sense once you push them past the Planck scale, the same way asking what colour a sound is, or how much a Tuesday weighs, are questions built from words that simply stop fitting together meaningfully once you push them into the wrong domain. Many physicists find this idea genuinely humbling rather than discouraging. Science has always operated on the assumption that better questions, better tools, and better theories eventually reveal deeper answers, layer after layer, all the way down. The Planck length raises the genuine possibility that down does not go on forever, that reality itself might have a bottom floor built directly into its architecture, a final layer where the very language of location, distance, and sequence stops applying, because the deepest layer of reality may not be built out of space and time at all, the way the previous chapters on emergent space-time and holography have already hinted. If that turns out to be true, it would hand science one of the most important discoveries in its entire history. A genuine, permanent boundary marking exactly where questions about location and distance stop applying, and where an entirely different kind of question, about information, connection, and whatever truly fundamental ingredient underlies space and time, needs to begin instead. Ask a 5-year-old what is the biggest number, and after a moment of thought, they will usually answer with whatever the largest number they currently know happens to be, before quickly realizing you can always add one more and beat it. Numbers never hit a genuine ceiling. There is no largest number, only larger and larger ones, stretching on forever without ever reaching a final, true maximum. Mathematicians describe numbers that behave this way as unbounded, always capable of growing further no matter how large the previous step happened to be, and for centuries physicists simply assumed every measurable quantity in nature worked the exact same way, without limit in either direction. Ask a physicist what is smaller than the Planck length, and depending on which chapter of this story they believe most strongly, you may get an answer that sounds shockingly similar to that childhood realization, except flipped completely upside down. Instead of no ceiling, there may be a genuine flaw, and instead of the question having an answer that keeps getting refined forever, the question itself might eventually stop making sense at all. This possibility puts the Planck length in genuinely rare company among scientific concepts. Most open questions in physics are difficult because scientists lack the data, the technology, or the mathematics needed to answer them yet. Difficult in the ordinary sense that better tools, given enough time, eventually crack them open. The question of what lies smaller than the Planck length may be difficult in a completely different way, because the question itself may be built from concepts, location, distance, smaller than, that only apply above a certain scale, and stop meaning anything useful once you try to push them below it. Several physicists explored throughout this story have compared this to a much simpler, much older example, asking what lies north of the North Pole. The question sounds perfectly reasonable using the same grammar as any other question about direction, and yet standing exactly at the North Pole, every single direction you could possibly travel already points south. North, as a meaningful direction, simply stops applying at that exact point, not because the answer is hidden or hard to find, but because the concept itself runs out of room to mean anything once you reach that specific location. The Planck length may work the same way for the concept of distance itself. This does not mean physicists have thrown up their hands and stopped asking questions about the smallest scales of the universe. Nearly every chapter of this story has explored physicists doing exactly the opposite, building loops, strings, holographic boundaries, and entangled networks, each one a serious, mathematically rigorous attempt to describe what reality might actually be built from once ordinary distance and location stop being useful concepts. What may be permanently retired, if these deepest interpretations hold up, is not curiosity itself, but one very specific, very old question, the one this entire story opened with. Not what is the smallest distance that has any meaning, but something even stranger and more final. Whether the question of smaller than the Planck length was ever a coherent question to begin with, or whether it was always, from the very start, a question built from words that simply run out of meaning at exactly the edge this entire journey has been circling. Look down at your own hands for a moment. Ordinary hands, made of ordinary skin, resting in your lap or wrapped around whatever device you're using to hear this story right now. Nothing about them looks remotely mysterious, and yet, according to nearly everything explored across this entire journey, your hands are standing on top of one of the strangest, least understood flaws in the entire universe. Every atom inside your body sits an almost incomprehensible distance above the Planck length, a gap so enormous that comparing an atom to the Planck length is roughly like comparing the entire observable universe to a single building. And yet, if the deepest ideas explored throughout this story are correct, that impossibly distant flaw is still down there right now, underneath everything you're made of, quietly setting the absolute limits on what your own body and everything else in the universe is even allowed to be. If space really is woven from discrete loops, then your hands, right now, are built from an almost incomprehensibly vast number of tiny, individual threads, stitched together so tightly and so precisely that nothing about their texture has ever been detectable by any sense you possess. If space is instead built from vibrating strings, then every atom in your hands is a symphony, an enormous, layered arrangement of notes playing out on instruments smaller than anything you could ever picture, blending together into something solid enough to hold a cup of coffee. If the holographic principle is correct, then everything about you, every memory, every heartbeat, every thought passing through your mind while you listen to this sentence might ultimately be encoded on some distant boundary, projected outward into the three-dimensional experience of being alive. Nobody currently knows which of these pictures, if any, is actually correct. That uncertainty is not a failure of this story, or of the physicists who have spent entire careers chasing this question. It is the honest, current edge of human knowledge, the exact spot where humanity's greatest theories, tested with extraordinary precision for over a century, run out of solid ground and hand the story over to raw curiosity instead. What remains completely certain, regardless of which theory eventually wins, is that a boundary of some kind exists, a scale where questions about distance and location stop working the way they do everywhere else, a genuine edge built directly into the fabric of existence rather than into the limits of human technology. You will never see it directly. No microscope, no matter how advanced, no collider, no matter how large, will ever show it to you with your own eyes. And yet it is there, underneath your hands, underneath every atom in every star, underneath the very first instant after the Big Bang, quietly shaping the outer limits of what reality is allowed to be. Somewhere on Earth right now, in university offices, in physics journals, in late-night conversations between graduate students who cannot let this problem go, people are still chasing the answer, adding new pieces to a puzzle first hinted at over a century ago by a physicist who was only trying to build a better ruler. The floor is still there, waiting, exactly as small, exactly as strange, and exactly as unexplained as it was in the very first sentence of this story.